All right, let's go ahead and get started. For those of you who don't know me, my name is Scott Newbold. I'm a member of the biology faculty here at Sheridan College. And this is the Museum of Discovery Science Lecture Series. This is the second lecture of this semester. We've got a lecture roughly once a month each semester on science topics that range all over the place, local, from bighorns, wildlife, geology, paleontology. So if this is your first time, there is a website on the college website, www.sheridan.edu/lectures, that has the schedule of both the Science Museum lectures and any others that are going on campus. So 2 more after tonight. So 1 in April and 1 in May. I was just going to give you the titles of those and the speakers so you can think ahead. April 12th, The Bighorn River Then and Now with Bob Crum. And May 3rd, A Passion for the Seed, the History and Science of Plant Breeding with Donna Harris, who's a UW plant science professor on campus here. So I'll go ahead and introduce tonight's speaker. Tonight's speaker hails from Bighorn, Wyoming, and is a graduate of Bighorn High School. He earned his undergraduate degree in biology from St. John's University in Minnesota and his PhD in molecular genetics from the University of Kansas. In 2005, Dr. Lindemann returned to Wyoming to grow his biotech consulting firm. Dr. Lindemann brings 30 plus years of experience to his role as Director of Life Sciences for RAMACO Carbon. During the last 10 years, Dr. Lindemann has been a consultant for RAMACO, with the last 3 having been as a full-time employee. Tonight, he's here to share with us updates on how RAMACO is leading the development of new carbon-based materials as the building blocks for the future era of carbon manufacturing. Please welcome Dr. Garrett Lindemann.
I grew up in the area. I remember when Sheridan College was small, now it's bigger. A lot of things have happened, and that's all good. One of the things we've seen changed, and since I graduated high school in the late 70s, is we've seen coal go from a thermal coal. And now RAMACO and a few other companies and some universities are trying to take the coal and make products out of it, advanced products out of it, just not regular products. I'll talk a little bit about the history of coal to products in a minute. So in essence, what we're trying to do is take $17 or $20 a ton sub-bituminous thermal coal in the area and make it into things that are like $5 a pound or more a pound. And there's a lot of things we can do with that. What you need to remember, or maybe you don't know, is our coal in the area is about, on a dry matter basis, about 50% carbon. And so we're made out of carbon, plastics are made out of carbon, the fuel you burn is made out of carbon. A lot of things are made out of carbon. And we can make advanced products out of that. So it's that process of trying to find something else to do with coal other than burn it. And basically at RAMACO, we have 2 sayings. One is coal's too valuable to burn, and the other is no molecule left behind. I think I've discussed why coal is too valuable to burn because of the carbon, and we actually call it a carbon ore. And there's no molecule left behind because with anything, whether it's oil or slaughtering an animal or something like that, there's always something that can be done with something else. We were talking about the Indians and the buffalo jump down by DeSmit before everybody came in. And the Native Americans were very good at using every little bit of the buffalo, every little bit of an animal that they slaughtered, hunted, and slaughtered. So we're trying to have that type of mentality at RAMACO. Sort of for your own signposts here, I'm going to play a video that we have at RAMACO. If you want to see other ones, you can go to the website. So I'll talk a little bit about the company after that and then get into the presentation.
Around here, we know respecting tradition doesn't mean forgetting there is a future. That's why at RAMACO, we're inventing a new foundation for Wyoming's economy and its families. For a decade, RAMACO has explored new ways to use the carbon and coal to create new and better products that people use. This year, to help grow, we announced a merger with our larger public partner, RAMACO Resources. In Sheridan, we've opened the world's first Coal to Products Research Center, working with our nation's best minds in carbon and material science. Silicon Valley was built in California. We are building Wyoming's own Carbon Valley, right here in Sheridan. Learn more at RAMACOCarbon.com.
So that's the video. Let me get back here to presentation mode. Please, as we go along, if you've got a question, raise your hand or interrupt me, mainly because it's going to be easier if I have the slide up to discuss it. We can always go back though, so if you have other questions, that's fine too. And I've got to figure out where I want to stand on this. In the video. So a little bit about the company. Of course, the parent company's back in Lexington. It has mines in Kentucky, West Virginia, Virginia, and Pennsylvania. Here, RAMACO Carbon is here in Sheridan. And like the video said, we've been doing this for about 10 years. We have our websites that you can visit if you want to. So we'll get into the presentation. I alluded to the fact that coal to products has been something that's been around for a little while. Actually, it's been around since about the 1860s, about that time, because one of the first products was this aniline blue, that one right there. And then also all of these other synthetic dyes. These were the first synthetic dyes. So they were not extracted from plants. They're actually man-made. And what happened is they basically had coal research going on, breaking it down, taking the individual chemicals, because since you're made out of carbon, you have a bunch of organic chemicals in there. And so you can use them and break them down and make them into other things. One of the ones was synthetic dyes. We also will talk about, coal tar here in a minute and some other things. But this just happened to be the most colorful slide that Bob found, because the other one's really ugly. So I'll show you the other one now. So I told you this was really ugly. This is from 1924. The other one, I'm not sure when it was from. I couldn't find a date on it when it was made. So we've talked about the colors. We get over here. As we go along here, you can see what the different products are made, how they're made. Fuel. So if we come from coal, break it down through direct coal liquefaction, indirect coal liquefaction, we can get coal gases, everything from fuels to diesel, to lubricants, to waxes, and we can get to what's called town gas. So basically the lamppost, the gas lamppost, town gas illuminated a lot of cities for a while. Coal tar. Have you ever used a black dermatological substance to help, pull the stuff out of a pustula or something like that? No one has? Oh, it's got coal tar in it. Carbonic acid right here, disinfectants, of course, wood preservatives. We get down to more dyes in this area and things like that. And so there's this whole tree tells you how to get to them. There's a bunch of other substances in here. Coke, of course, coke is important to making steel.
Hey, Garrett.
Yes.
Or Dr. Lindemann.
Sorry, Garrett's fine. Actually, I hate to say this, the only Dr. Lindemann I recognize is my father. Okay. Because every time I hear Dr. Lindemann, I go, shit, Dad's alive. So, yeah, Matt.
So to go from a coal to the other products, it's pressure and limited oxygen to get to those other products. Is that how you? Well, it's just not, you're not going to dig it out of the ground and.
Right. Yeah, you have to process it, and there's a variety of different ways of processing it to get where you want to go. Okay. And one of the things that we're going to be talking about a little bit later is here's the pitches, because from the pitches you can make carbon fiber. Sort of the interesting thing about the different oils and gases and diesels is Sasol in South America basically did this for 50 years. They were going to build a plant in the southern part of the US. I don't think that ever got built. And this is the way in World War II that Nazi Germany was able to survive without having a whole lot of petroleum. They used the two different methods to generate aviation gas and motor gas and diesel and lubricants. So our product areas are carbon fiber, bulk graphene, porous carbons, building products, monolayer graphene, and rare earth elements. Carbon fiber, of course, the whole goal here is with carbon fiber, is to make a lower cost, better product than what you can get from oil. So a lot of these products will come from oil. Plastics come from oil. You can make plastics from coal. This is what the Chinese do. They take and gasify it, make it methane, make it into methanol, and then they go through the process to get to the point where they have plastics. You can do the same thing with oil. So we're doing it we've done it with coal. And in the past, in fact, the first plastic was Bakelite. The old cue balls were made out of Bakelite. Maybe some of us had phones that had Bakelite covers or toasters with Bakelite covers. It's all the rage. So if you go to a Brandian auction, they say Bakelite, everyone's like, yeah, I'll buy it. So the pan fiber from oil is about $10 a pound. Is that still right, Bob? Is that $10 a pound now? So we're trying to shoot for a $5 a pound product. We're trying to make it a structural composite, so we can build things like, car shells, hoods for cars, aircraft material, and then there's some applications in infrastructure like repairing bridges and making items for bridges to make them better. We also are looking at using it to insulate or activate it for industrial and consumer applications, such as dehumidification. We did a concept paper earlier this year with the city of Manchester to actually use modified isotropic pitch generated fibers to help purify their water. Actually, I'm sorry, their sewer effluent into the Tongue River. The difference here is this needs to have more graphitic material in it to be able to make a stronger fiber. This is basically sort of less graphitic material, and you sort of blow it like cotton candy. If you've seen a cotton candy machine, you can electrospin it, or you can actually do another process called melt blowing, which is sort of like you just sort of blow it out into piles, and then you use it after that. The bulk graphene, basically it's coal. We treat it through, we have a couple different ways of doing it. The current way is a salt process. And the goal here is to make lower cost additives for concrete, paints, coatings, composites, and inks. This material is magnetic, conductive, electroconductive. So it can go into inks and make electrical conductive inks. Coatings and paints. So the material helps decrease the wearing of the paints. It also increases the antiviral and antibacterial properties of the paints. For concrete, we're actually putting it in there trying to increase the strength. So by increasing the strength, you decrease the amount of cement that you have, which decreases the weight needed and the cost, and also decreases the CO2 into the environment, because one of the higher generations of CO2 to the environment is the generation of cement. Porous carbons. This is a pretty direct process. You're basically taking these carbons and putting holes into them so they're porous. The goal here is to use it as a catalyst or purification applications or supercapacitor. Building products, carbon foams, bricks, actually lighter than concrete and stronger than concrete. And it can, if I remember correctly, it can actually be molded. So you can put it like a lathe and cut it in shapes. Monolayer graphene, this is my favorite topic here. We're basically taking coal and making it into graphene. And graphene is a two-dimensional material, so it's like a paper sheet. And it looks like chicken wire. If you can see, it looks like chicken wire. And what you want to do is put it down in that monolayer material so you can lift it off and make biosensors out of it. We'll talk a little bit more about this, but it also has applications in computers and electronics, personal electronics. Right now, the one that we're really excited about here is rare earth elements. These are a group of 17 elements. And since I know we all have computers and cell phones, we have rare earth elements in our pockets and in our satchels and stuff like that, because they're used in defense electronics, they're used in magnets, they're used in personal electronics and supercomputers and stuff like that. China controls 85% of that right now. So there's a big push to find different resources for REEs. There's an ongoing mine that's coming on board over by Hewlett with a processing facility over by Upton. And there's other ones going in too. So we're currently in the process of looking at the reserves that we have. But that runs right with the coal, and the coal across the US does have REEs in it. But there's differences between where they occur back in the eastern coals versus our coal out here. So like I've been talking about, we want to take raw coal, very inexpensive, 3 cents a kilogram. A kilogram is about 2.2 pounds. Make it into metallurgical coal, so we increase the value of it by about 5-fold. Here with coke to make steel, we've increased it by about 8-fold. Coal tar, we're going up in price, and so from the coal tar, now we make pitches, and that price increases even more. And then we go to mesophasic pitch, so high graphitic quality, a mesophasic pitch, and by graphitic quality, I mean the graphene occurs in it. We have ways of measuring the graphene and visualizing it. And the textile process to go from the coal pitch or the coal tar to the carbon fiber, I mean, you'd basically melt this and make a thread. But once you get that thread made, and then you treat it, so you have to oxygenate it and carbonize it to make it hard, so you can actually use it. This textile process is as old as textiles itself. I mean, if you've ever been to Buffalo woolen mills and seen their process, it's a very similar process once you get it onto the spindles. So here we are with coal to carbon fiber. Currently, we've just finished up these 2 grants right here. Charles Hill, the one leading this right now, is Charles, the one leading it. I shouldn't imply that he's going to be axed or something like that. We have sourced the coal, or sourced the material from a company called HTI Axons, and basically we were looking at ways of increasing the graphitic material in it. And if I remember correctly, this is a microscope image of it, and the purple material, if I remember correctly, is the graphitic material. And so we look at that, or Chaz looks at that, then estimates the percentage. And so he's trying to get a higher and higher percentage. I think the highest he was able to get was about 20%. So it's really best used for the melt blown material, the electrospin material that we use. It's not going to be a high quality carbon fiber material, but we've sent some of our other coal from back east over to HTI Axons to generate us some more pitch. And Chaz has a process of looking at that and attempting to make more higher graphitic material for mesophasic pitch. We have this device here called a Randtassel. They put the mesophasic pitch in here as a solid. It basically melts it, extrudes it, and we put it onto this roll here. So this is different runs of the pitch for Chaz that Chaz has extruded and spun onto this. And then he takes and mounts it onto these little devices here. So in the middle you have a fiber. And then he takes and stretches it and looks for changes in strength. And that's what these graphs are all about. So again, structural fibers, here's his machine here for determining the structural strength of it. And so again, the structural fibers, again, automotive applications, wind power, aircraft, infrastructure, marine, and sporting goods. And so his view on the blades of the wind turbines is to actually use it here in what they call a spar cap. This is your piece of metal here, and so this is the spar cap here to reinforce that. Because carbon fiber is lighter and stronger than steel, lighter and stronger than aluminum, and more conductive than copper. So activated carbon filters, we talked about a little bit, air and water filters, industrial processing filters like capturing organic volatiles that come off a process, say a gluing process or some sort of other process like that. CO2 capture, we're looking at how we can use this to capture ambient CO2 and do carbon capture. Insulating fiber, industrial furnace. He's also said that this could be used for the nozzles on spacecraft and missiles and things like that, because your nozzle needs to move to change the direction of the missile or the rocket. And then we've talked a little bit about the building insulation here, and here's especially aerospace. The porous carbons. So we're basically taking coal and treating it and then baking it and washing it and then testing it to see how much porosity we get in it. So we want, depending on the application, we want big cavities and a lot of them versus small cavities and a few of them. And this would be used for things like, catalytic support. Bob worked for a company that made catalytic converters. So it'd be like, the catalytic support for that. We can do electrical capacitors. Here again, we're talking about absorption and desorption of things like CO2 or other materials as a purification for water, because it's basically an activated carbon. Almost all water plants that I know of have activated carbon filters in them that they move around and change out. And drug delivery, there is actually a university that used this as a drug delivery to prevent the application of a antiviral to an infected eye every day. So okay, so this is what we refer to as graphene A, nanostructured carbons. This is for applications into concrete and paints and inks and other coatings. So here we are. Okay, good. Now I'm back on track. Is there a question? I hear a question or just a comment? Okay. So like I said before, these are conductive inks. We talk about how big the market is. It's 3.3 billion, but that was back 4 years ago. Doing other composites, it's pretty big still, 13.1 million. Paints and acrylics. So basically, again, putting this into a paint or a coating on, say, the underside of a boat will keep the barnacles from binding to it, and it will toughen up the paint and also increases the antiviral, antibacterial material on it. Concrete additives, this is the one that we're sort of really working on right now. Like I said, increases the strength. So here we are, monolayer graphene. Like I said, we're taking raw coal, and of course, raw coal it's more complex than just a lump of coal. As you go from the lower ranks of coal to the higher ranks of coal. So if you go from peat moss all the way through up to anthracite and graphite, and I think diamonds have now been added to the rank of coal, you see an increase in order and a decrease in sort of like dirt and other things in it. So sub-bituminous coal is about halfway between that. So you get graphene-like material in there with other dirt and other amorphous material. And so what we need to do is we need to take this $17 a ton material and make it into a material that is, a 3x3 square is worth about $300. I can't remember what the price is on the tonnage. So the way you do that is you basically vaporize this. So we use this device here. We've got different gas flows here. We have an oven here that we use as a programmer. And inside that, we put this little sled here with our coal at one end and our copper at the other end. And copper is the substrate where it lands. And a little bit closer look at it. So this is the process of getting the copper ready to be to be evaluated through a process called Raman. We use the copper because what happens is it helps to catalyze the reaction of going from larger organic molecules down to smaller organic molecules like graphene. And then we use a Raman device, and we look at this. This is basically like this little square here we cut out under a Raman device, and we try and find areas where we can find high quality graphene, lower quality graphene, and this amorphous graphene. And we look at the Raman spectra here. This is monolayer graphene with defects. So it's not perfect, but it's monolayer graphene. And then part B here in here has multiple layers. So that can be anywhere from 5 to 50 or 100 multiple layers of graphene in there. And this is just amorphous carbon. And so it's just leftover sort of carbon schmutz from the process. There's still uses for multi-layered graphene. It's not, it is of value, but this is what we were shooting for. And now rare earth elements. We're looking at, how much we have, what we have, where it's located on the mine. The value of it is rather stunning. I mean, some of this material goes for $14,000 a ton. Is that right, Bob?
Scandium's up about 1.3 million a ton.
1.3 million a ton. Okay. So, and that's this one right here, scandium. Neodymium is right here. It's one that's used in magnets a lot. So they all go into electronics and have all kinds of applications, electronics. What's interesting is they're now finding proteins in biological systems that bind these. And there's uses for these in cells and bacteria that like anything else in your body that picks up a metal, iron for your blood, other ones to make your enzymes work, things like that. So they're finding that these actually have a role in biology too. Plants pick them up, we pick them up. So we're in the process of looking at what we have, where it is, how we're going to refine it, what the yield's going to be on that, because that will determine the profitability in mining it. Now we're on to carbon foam. And yeah, you can, Chris can generate these in a block shape. You can generate them in a cup, so they look like sort of like a dome, like an igloo. It's a matter of the foam you put it in. It's low cost. It's pretty inexpensive to make. Like I said before, you can go ahead and lathe it and cut it and do things like that with it. And then you can use it like a brick. You can glue it together and use it like a brick. Ours is from coal. UW made a house of carbon bricks made from char last year. So here's sort of the economics of it and the driving force behind it. It's lightweight. It has a high compressive strength. It's an insulator. It's also fire resistant too, corrosion resistance, electrically conductive. But so the carbon foam, its density is 12 to 30 pounds per foot cubed. You've got brick at 100, 120, and concrete at 150. So it's more than 10% less than carbon foam is 10%, at least 10. It's only 10% of what concrete is. Your strength, of course, 3,800 pounds per inches squared. That compares very nicely with concrete down here. Then this is high strength concrete down here. So the stuff that goes into bridges, highways, pillars, the weight sink on buildings. You can also use it for, like I said, it's fireproof. It's bulletproof, so it can be used as armored panels or even for armored personnel. You can put it into a plate. It's great for heat transfer. The heat transfer thing's pretty crazy. You can put something hot on one side and it feels cool on the other. And it actually has sound dampening qualities too. So it's sort of an uber material. So our commercialization plan for any of these is to, you know, find and make these as cost effectively as possible. In fact, it's a reoccurring theme in our commercialization meeting, which is tomorrow afternoon. You know, what does that do for our cost? What does that do for our margin? You know, how do we deal with the different costs in doing things? Is that too expensive to do? In the case of the REEs, you know, how much are we going to get out using these different refinement techniques? Because refining something's never 100%. And then that helps. And then just sort of the cost of doing business and the technical risk, the economic risks are all then compiled to decide whether or not they're going to, the economic plan for it. Or is RAMACO itself going to move forward with it? Is there another way to make money with it? You know, do we partner with somebody? And that's it. So, questions? Sure.
So these experiments are being done with coal. Is any of that coal that is there down where that IC building or whatever it is that coal being used?
Yeah, so the actual mines on the other side of the highway?
Well, no, you have, well, I guess I'm not sure where okay, what coal is being used? Is the coal being used, is it all within this area that you get that coal from? Or do you have to bring it in from somewhere?
No, the goal is to use the coal. So the ICAM is right below the port of entry, down there along the Tongue River.
Correct.
Okay, so on the right-hand side of the highway, as you go to Ranchester, a lot of that property is RAMACO and a future mine. Okay, the plan is to use that coal to do this. Now, like with the carbon fiber, I mean, we can use our coal to make the isotropic insulation like carbon fiber. You know, not the structural, because we can't get the graphitic material high enough in it to make it strong enough. So we brought in coal, just buckets of it, 5-gallon buckets of it, from mines back east that are owned by RAMACO.
Okay, but are you using any of the coal from around here then?
Yes,
Oh, okay.
that's what we predominantly use.
And then as far as coming up with any product to date, is this all experiment or has anything concrete as far as product been developed to this point?
Please describe for me what you mean by experimental, because I'm a researcher, I'm an experimental researcher, but we're doing applied research with this.
Okay, you're doing research, but to date, has anything concrete as far as an actual product that can be used, sold, has anything been developed? Or is this all research to this point?
No, okay, so to me as a researcher, there's just straight up academic research where you say, I want to look at this, or I believe that this is the hypothesis. We're not doing that. What we have is a product, and we have paths forward to products. So we're doing more of applied or developmental research. And the question now becomes, is the economics around that product make sense to make a product? And then the question becomes, you know, how much is it going to cost to make that product, to build out, say, a factory? And then the question becomes, do we partner with somebody? Who do we find to buy it? Now, we have a couple products that are in the process of being evaluated by potential customers, you know. And so for the ICAM to be there for only a year, that is a significant step forward. Because before, everything that I was doing for, you know, the last 10 years for RAMACO was, hey, if we take a ton of coal and make it into nanowires or graphene or something else, what is the value of that? So it was a scoping, if you will, a scoping study. You know, how do you want to do it? Where do we want to go with it? And then, you know, the questions then became, you know, who do we want to partner with on the university side and the national lab side? and things like that.
Okay, so then at this point, okay, so you're doing your research, so, but at this point, but right now, there are a couple of items that are being
Evaluated.
evaluated by,
by
to see
customers.
if it's profitable.
Yes.
Okay.
Well, yes. Yeah.
Okay.
I noticed on one of the slides, it mentioned some process that was licensed from the Department of Energy. Have you guys developed any proprietary processes or patented processes that that'll help to develop these products, or is that part of what you're doing?
Yes. So I think the number I last saw was there's 12 granted patents, and there's several patents that are in process. But the process with working with the national labs is you enter into an agreement. And so you work with them. If a patent comes about, you then have first choice to in-license it, to bring it in-house. So that patent, I think we worked with them and developed it and have first right of refusal on it. I don't think that we actually licensed it from them. It doesn't mean, we've looked at universities that have patents, around coal, West Virginia being one of them, Kentucky another, that have patent portfolios that can be looked at and may or may not be open for licensing. Yes.
The rare earth elements, are they just kind of randomly distributed throughout a piece of coal, or are they like in veins like other elements are, like metallic elements?
Yeah, like gold and silver and copper.
Silver and copper,
The ones over by Sundance are in vein, right? Yeah, they're
Hard rock.
Hard rock, yeah. There's a couple of places that have hard rock.
Okay.
Ours are sort of sprinkled throughout the coal, and it's not really in the coal, it's in the surfaces adjacent to the coal. Now, and I think back east in the mines back in West Virginia, I think it's sort of the same thing. Why it goes from sort of this sprinkle to hard rock is a geological question that I can't answer. I've heard a couple explanations for why ours is that way, and that's because a volcano erupted and sprinkled it across the area. But let's keep in mind that coal came from a swamp, right? Prehistorically, it was a swamp. Plants picked this up, the animals picked up these REEs and used them and evolved to use them. So, maybe that's an alternative hypothesis that now it's fossilized and it's in there, much like the phosphate and the nitrogen and the sulfur that's in there.
So
Let me get my phone over in this side.
Yes, I had a follow-up on the rare earth elements question. So have you been looking at like the core samples that you all took for when you did the exploration for the coal mine, or like did you get a separate exploration permit from DEQ? Or?
I can't answer any, that's outside of my,
Okay.
I don't know anything about.
Yeah, I'm just curious because you kind of made a generalization about the entire mine area having rare earth elements. I was wondering, what's the basis of that generalization? Like what kind of actual samples you have from the strata?
I don't know how we got into the REEs. I was focused on something else at the time. I've been recently pulled into that. I haven't asked that question. I know because I've seen the data set, there was a bunch of core samples done early on a couple of years ago. And actually part of it was actually sort of legacy from a purchase of, I think, Bighorn coal.
Wyoming coal, but yeah.
Yeah. Whatever, yeah. And now we have new ones that we're boring and looking at and whatnot. And that's gridded throughout the planned mine. So, but when it comes down to permitting, I'm a research scientist. And in fact, this is the crazy thing about it. I'm a geneticist. My thesis was on differential gene expression in a mouse model for a human disease called polycystic kidney disease. Right now, the number is 1 in 400 people have it, and each family has a different mutation. I still keep in touch with that group because it's an interesting disease. But I was doing what they now call transcriptomics before they called it transcriptomics. I had to do it the whole old way. I did a stint as working on peptide molecules as drugs. I worked for a cosmetic company out of Madrid, a pharmaceutical company out of Madrid, Carl Zeiss, the microimaging side. I'm still involved with helping found and develop a digital pathology company in Budapest. You can look them up, 3D Histech. They're probably the best digital pathology company in the world. See, Nestle did a nutrigenetics project with Nestle. And when I was at Roche, I found the device that was then called Roche Light Cycler. They just quit making it about 4 years ago. I was with Roche in the 90s. I wrote the white paper that caused Roche to buy a company called Ventana Medical Systems, which is a big pathology company. You know, GlaxoSmithKline. I've done some regulatory stuff. You know, so it's really strange for me to go from being a life science guy, a geneticist. You know, I'm used to working with cells and things like that to be going over to be working in coal. But the interesting thing about biology right now is, and it always has been, this blended science. It's not a pure science. It's not math. It's not physics. It's not chemistry. It's a blended science. So it's biochemistry, cells, cell biology, a lot of electronics now, a lot of computer work going on in it, in looking at the toxicity of drugs and looking at models and whatnot. A lot of biophysics, a lot of physics going on in it, you know. So it's a real blended sort of area. And that's probably helped me survive being in the coal industry. So it's sort of strange. What's even stranger is growing up here. I mean, my folks moved here in '68. My dad was a radiologist in the area for 30 years. I remember in '72 when Decker Mine paid everybody in $2 bills because people were complaining about the dust in town and everything else. And that sort of shut the whole town up at that point in time. You know, I'm sure people in here have relatives or work for the coal mine or have some business that's ancillary to the coal mine. You know, Matt used to probably have a bunch of coal miners on as checking accounts at First Interstate. You know, so it impacts the whole area. But until I started working for RAMACO, I was like, oh, it's going in the coal cars and we get burnt. You know, even back then, I mean, I've showed you, you know, even back in the 1860s and 1920s, you know, that they were making aspirin and other medical material out of it. They were making dyes out of it. And the interesting thing about the synthetic dyes is these were the first dyes that could dye silk and some other cottons. Before they couldn't do it.
Everybody had brown clothes.
Everybody had brown clothes, or white clothes, you know. So, and then you look at things like carbonic acid, which the English physician said, well, you know, Pasteur said we need to be more sterile about things. You know, Pasteur, and so he used carbonic acid to clean his surgical instruments and clean the wound, and it showed, you know, great potential. Dr. Semmelweis in Budapest at Semmelweis University said, well, if you're just going to clean the wound and clean the utensils, we should use it to clean our hands and clean the whole room, you know. So, and the interesting thing about that is the basis of Listerine. You know, aspirin is still out there. They just don't source the ingredients from coal anymore. I mean, they source it from other things. They now actually source it from petroleum. And if Charlie Atkins was here, Charlie would tell you the big difference was there between pre-World War II and post-World War II was the fact that the Department of Defense funded what became fluid cracking for the oil company. So it was king coal. I mean, we made fuels from it. We made everything else from it. You can take the weathered coal and put it on your garden, and it improves your garden because it contains carbons, nitrogens, phosphates, sulfurs, everything your plants need. It's not a synthetic fertilizer that you'll see things jump out of the ground, but it's a more natural fertilizer. So there's a lot of benefits to the coal. Carbon black, we have black tires. It helps harden the tires. It goes into black inks to make the inks black. Mascara, I see some women in here, mascara, it's got carbon black in it. And I talked a little bit about the dermatological applications of coal tar. There's black material for that. You can actually get toothpaste that's made from coal. And so now, you know, and that's why we call it a carbon ore. Because there's a lot of things that can be made from it. It's stunning that you can make things stronger than concrete, stronger than steel from carbon. It's stunning that you can make all these different colors and all these different fuels from coal. And it's not just coal. I mean, a lot of this is already being done with oil. I mean, what you're doing is you're starting to use a source that we have in significant abundance. And for every ton of our coal, it's equal to about 3 barrels of oil. So what's a barrel of oil now? 80 bucks a ton, 80 bucks a barrel, excuse me. So that's $240 a ton of sub-bituminous coal here in Wyoming. I haven't looked at it. Let's say it's 20 bucks. You know, methane. The way the Fischer-Tropsch system works to make diesel fuels and things like that, you can take the coal and gasify it. GE has a gasifier, make it into methane, use the Fischer-Tropsch system and make, you know, your diesels and lubes and a lower quality gasoline out of it. So, I mean, that all exists. And like I said earlier, you can take that gasifier and take that methane and make it into methanol and make other organic compounds out of it and get to everything from, you know, alcohol that you could drink to plastics, to anything else you want that you can think of that is organic. You can make fertilizers out of this. You can make chemical fertilizers out of it if you wanted to.
Most of your clothes are made out of coal. All the polyesters, polyethylene you buy from China comes from coal. They don't use oil.
And they're building how many coal plants a year?
One every 3 weeks.
One every 3 weeks. And that's without the Belt and Road Initiative, right? Yeah. So, yes.
I have a more basic question. You said that the coal out here is about 50% carbon.
Yeah.
Well, how do you get from coal to 100% carbon fiber? What do you do to it?
Well, that's why you go through the process of liquefying it and make it into a pitch, because as you liquefy it and make it into a pitch, you get rid of all that other stuff.
Where does that go?
20% is water.
20% is water,
Okay.
but everything else, you know, I mean,
Amorphous stuff that doesn't make nice pitch, then we can go to the building product side or the, you know, make other things out of that. That doesn't go into the pitch.
they actually distill it to get to the pitch, right? So you have a pot and you just bake it and then you distill it and it comes up and goes over and out. And that's pitch. Everything else that's left behind is, you know, stuff that's left behind that they play with.
And what's pitch exactly?
Basically coal tar. It is a very sticky tar.
Okay. And then how do you get from that product to a carbon fiber?
Squeeze it through and you make thread out of it. And then you oxidize that thread.
You carbonize it.
And then you take it up to high temperature. And so it basically gets very, very, very strong. And what are they running, about 8 micron diameter? I forget what the hell.
Yeah,
it is.
I think 8
It's
micron.
very, very fine. And then you take, like you would a fiberglass fishing rod, you take this one little fiber and you wrap it together with 12,000 other little fibers.
Sure, yeah, I understand
then-
after you get to the fiber
Yeah.
part, but so you oxidize the fiber?
You oxidize the pitch. Sorry, take the pitch out, extrude it, and then you basically run it through an oven.
Okay.
And the oxygen decorates the surface. And then you take that through another oven and run it at very high temperature. And that turns everything to graphite. And that's where you get your strength.
Okay.
And then you wind it up. And you actually have to do the sizing of what they call it so that it doesn't stick to each other. And there's other treatments involved. Basically, it's you know, what you make your Corvette hoods out of. It's you squeeze that fiber and like you would at a fiberglass mat, and you put resin on top of that, and then you've got, you know, incredible strength and lightweight.
It's the same sort of thing. You can lay it in different directions like you would in an OSB board,
Mhm.
and then you're doing carbon fiber, so you increase the strength of it too. Any questions from the Zoom audience, Scott?
No, there's one that I can answer. She's interested, but she can share this. So this will be recorded and
Okay.
the link so that you can share that.
Okay, good. Anything else?
I had a question, actually, especially referring, because you were getting into the process of like carbon fiber parts, things like that. I've worked previously in vehicle repair, and some of that has been in like the high performance. So a lot of them do incorporate a lot more carbon fiber parts because, I mean, especially when it comes to high performance, they're rebuilding the engines all the time anyway. But I know one of the problems with that in the past, because of the way that it does have that higher compression strength. But one of the weaknesses with that is that it depends upon which axis you're experiencing that. So I don't know if there's been any promise in terms of like being able to sort of go about maybe perhaps restructuring it in a way that can sort of like give it a little bit more resistance to that sort of like side loading forces.
Well,
Talk to the
okay.
guys at Boeing. They make the 787s out of it.
Well, yeah, that's what 80%, that's like 80% of the plane.
Some
And the wings come up like this and touch. Each of them, I've been told by Boeing engineer I know. So, yeah. Yeah, the F1 racers are like nearly 100%
Right.
carbon fiber now, even the engine.
Right.
You know, again, not an engineer. You know, I hate to say that. I was gonna say, I think you just, you know, and then it depends on, are you looking at young moduluses? Are you looking at torsion strengths and things like that? So,
Okay.
I think if they were able to do it with fiberglass, they can probably do it with carbon fiber.
In terms of being able to mitigate the sort of like inherent weakness with side loading.
I would think so, because I would think that they solve that problem with carbon, with fiberglass,
Okay,
you know?
that's true.
So I think there's a process by which they could go ahead and do that.
Okay.
You know, again, not an engineer.
Gotcha.
Yeah, so.
That's what I'm hoping to become.
An engineer, okay, good.
Yes, sir.
The world needs more engineers, so, yeah.
Any more questions, Garrett?
Good.
All right, well, thanks a lot for coming.